Dear colleagues, good evening and warm welcome to Luxoft LTS webinar. Before we start, a few words about our agenda today and our speaker. In a few minutes, Rex Black will start his presentation. His speech will last approximately 1 hour, and then we will have questions and answer section. You have an opportunity to interact with our guests through the WebEx client. There is a section at the bottom at the right side of your screen where you can post a question to our speaker. Rex will comment and answer after his presentation, and in case of many questions, you can also contact him directly via LinkedIn or his Facebook page. Also, if you'd like to know about our latest news and events, please follow our pages on LinkedIn and Facebook. And now I will let Rex Black to introduce himself. One more time, thank you all for joining us tonight. And now, Rex, it is your turn.
Hello. Thank you, Tatiana. I'm assuming that my screen is coming up now. I see that I've been made the presenter. So welcome, everyone. I am Rex Black, president of RBCS. We are a worldwide software testing and quality assurance consulting, training, and expert services firm based in the United States with clients around the world. We help our clients in improving their testing, making themselves more effective and efficient with training people, including ISTQB training, and with doing assessments and longer-term consulting as well. So I've been in this business, in the software business in general, for about 35 years. I've spent most of that time in testing, and I've been a test manager, test engineer, automation test engineer, played a lot of different roles. But for the last 20 or so years, I've been working as a consultant, and actually almost 25 years running RBCS, my company. I'm also the author of 13 books on software testing and past president of the ISTQB and the ASTQB. So today's presentation is on pairwise testing techniques, and this is a part of a larger series of webinars that I have done through our company, and will probably repeat sometime over the coming year or so. It's adapted from the Advanced Software Testing Volume 1, which is a test analyst and test engineers book. The foundational test design techniques are equivalence partitioning and boundary value analysis, which are very good by themselves for doing things like input field validation and so forth. Now, one problem that sometimes arises is if you look at the number of input fields that you have on a screen, for example, and you say, well, let's see, there's, say, 5 equivalence partitions for each input field, and you've got 10 screens, or 10 fields on the screen, excuse me. If you were to try to test all possible combinations, that would be 5 to the 10th power of combinations. So equivalence partitioning is great, except that it breaks down when you start to think about, how do I go about testing interactions? So there are basically 2 paths that you can go down here. One is if you're in a situation where you know how the fields, the input fields or other conditions, which they don't have to be input fields, they could be any number of things. If you know how these input fields or other conditions are supposed to interact, then you can analyze the interaction, for example, using a decision table or using a technique called domain analysis. But what if these fields or conditions or configuration settings or what have you are supposed to be independent and they're not supposed to interact, but you are afraid that they would? You're concerned that there might be some inadvertent interaction, and that would lead to misbehaviors when people do certain types of things. So this technique that we're about to talk about, pairwise testing, is a technique that you can use to try to find situations where pairs of factors are interacting in an undesirable way, and yet at the same time not subject yourself to a situation where you have to test 5 to the 10th power of test cases, which is, clearly impossible. So again, the basic concept here is that we are dealing with unconstrained and independent factors. In other words, the factors can vary independently of each other, and they take on different options. These can be, again, the options can be thought of as the equivalence partitions for an input field, but they can also be the equivalence partitions for a configuration setting, which is the example that I'm going to show you in a minute. And what we're going to do is construct a table that contains combinations of options for each factor that we're interested in. Table is generated using either a orthogonal array, which you can download off of the internet, or using a tool. You are guaranteed to get all possible combinations of options across all possible pairs of factors. But notice that I said pairs of factors, not all combinations of factors. It's all combinations of options across all pairs of factors. Now, you might say, why do we do that? Well, there has been some research done on this, for example, by the United States National Institute of Standards and Technology, that shows that from a testing point of view, misbehaviors are most likely going to be associated with a single option for a single factor, or a pair of options across a pair of factors. But higher order combinatorial problems are much less likely. So in other words, a failure that is associated with a particular three-way combination, this option for this factor, this option for this other factor, and this option for yet another factor, those are pretty unusual. Now, again, we are talking about situations here where the factors are not supposed to interact. They are supposed to be independent. If you are testing a situation where the factors are supposed to interact, you should not use pairwise techniques, because the pairwise techniques will not deal with the deliberate interactions. They're not able to find that. There's nothing in the technique that analyzes the interaction itself. The assumption is they're not supposed to interact, but they might, and we want to check for that. And we want to check some reasonable subset of the total number of possible combinations, which again is likely to be in the thousands or potentially hundreds of thousands or even millions, depending on how many factors you're dealing with and how many options for each factor. So there are two techniques. One, as I said, is the use of an orthogonal array, and the other is using a tool. Now, there are various libraries of orthogonal arrays that are out on the internet, and I've included an example here of one reliable source. I would recommend not just going to any arbitrary website that has orthogonal arrays and going, hey, I'm going to download an orthogonal array from here. Bob's illegal pirated video download shop and orthogonal array repository, probably not the most reliable place to get an orthogonal array. So I would say this is a good source if you decide to use the orthogonal array technique. But what you'll probably do is end up using a tool. Now, I'm going to demonstrate this concept with orthogonal arrays because it allows me to explain this idea in a more clear fashion, I think, than just I put it into the tool and Shazam, magic happens. But once you understand the magic that's happening, it's probably going to be better and easier for you just to get a tool, unless you have some sort of weird rule in your organization where you're not allowed to use open source or free tools. There are commercial all pairs tools that are available. Again, this pairwise.org website that you see here is a one-stop clearinghouse for pairwise testing techniques, or testing tools, excuse me. But I would strongly recommend against paying for something. I mean, I don't know what obstacles would exist in your company to using a free tool, but there is a perfectly good free tool available from the National Institute of Standards and Technology in the United States. It is available for download worldwide. There are no export restrictions on it whatsoever. And I think you can probably trust the National Institute of Standards and Technology to not put malware in your system. If you don't trust them, then fine. It's an open source Java app, and you can look at the Java code. The jar file is included, so you can actually take a look at it. But going out and spending thousands of dollars on a pairwise testing tool, yeah, when this free one is available to you, is to me not a wise use of money. Now you might say, okay, orthogonal array, all pairs technique, all pairs tool to build an all pairs table. Is there any difference between them? There can be, depending on the tool that you use. Most of the time, this difference would not be important. It has to do, the potential difference has to do with the number of times that a particular pair of options will be represented in the table. Orthogonal array, you're guaranteed that each pair of options will be represented exactly the same number of times. In an all pairs tool, you might or might not be guaranteed that. That has some implications if you were to decide to use this to do, say, performance testing. But what I'm going to talk about here is the use of this to do compatibility testing and portability testing. And in those circumstances, you really do not need to worry about this issue of what's called array balance. It's not going to be relevant to the problem that you're trying to solve. Okay, so with that all said, let's take a look at our first example orthogonal array. So this is the simplest possible orthogonal array. What you see here, well, just to be clear, the orthogonal array is, I'm trying to find a, yeah, here we go, annotation tool. This portion of the orthogonal array is the actual, of the table is the actual orthogonal array, okay? The other parts are parts that I put around it to explain what the array is. Now let's see if I can actually remove the annotations here. Okay, no, not want to let me do that. Okay, well, we'll leave it up for the moment. In this orthogonal array, there are two factors, which here are labeled factors 1 and 2. And there are two options for each factor, which are 0 and 1. Okay? And if you look at the array, each pair of options is, across the two factors, is represented in one and only one row. So the first row has 0 with 0. The second row has 0 with 1. The third row has 1 with 0, and the fourth row has 1 with 1. Now, you might say, okay, I see that. That's not really all that surprising or interesting to me, though, because 2 times 2 is 4. So I would expect that there would be four possible combinations there if every combination is represented. Every possible combination of options for every pair of factors is represented. There's one pair of factors, and 2 times 2 is 4. Okay? So, yes, at this point, it's not all that remarkable, but wait a second, because we're about to see where the magic comes in. So let's take a look at a slightly larger one. Yeah, that's what I was afraid it was going to do. Sorry, I'm going to need to figure out how to delete this. What's that? Erase. There we go. Clear all annotations. There we go. Okay. So now we have three factors in this particular table, and I'm trying to get this thing ready to annotate again here. So factors 1, 2, and 3 are shown here at the top. And each factor has two options, 0 and 1 again. All possible pairs of options are shown across all possible pairs of factors. Now you might say, how can that be? 2 times 2 times 2 is 8. Well, let me explain here. First, let's satisfy ourselves that all possible pairs of options are present across all possible pairs of factors. So look at columns 1 and 2, which is easy because they're adjacent. And so again, here we see 0, 0, 0, 1, 1, 0, 1, 1 in rows 1 through 4. See that? Okay, so those are all there. Now let's look at 2 and 3. So 0, 0 is in row 1, 0, 1 is in row 3, 1, 0 is in row 4, and 1, 1 is in row 2. So again, they're all there. They're in different rows than they were in the case of factor 1 and 2 pairing, but who cares? Doesn't matter. We're going to test all of these things, and the order isn't important when you're doing a configuration test. At least it shouldn't be, because again, these things are supposed to be independent. So now let's look at column 1 with 3. 0, 0 is in row 1. 0, 1 is in row 2. 1, 0 is in row 4, and 1, 1 is in row 3. So as you can see, for all three possible pairs of factors, 1 with 2, 2 with 3, and 1 with 3, all possible pairs of options are present in one row. So we added a factor which had the same number of options as the other two factors, and it did not increase the number of test configurations. Now, again, you might be looking at this going, really? So, I mean, I'm not quite following, because 2 times 2 times 2 is 8. Shouldn't there be 8 rows? Well, again, remember, we are focused on pairs here, not triples. Okay? We're not looking at the three-way combination of factor 1 with factor 2 with factor 3. We're not doing that. We're looking at factor 1 and 2 together, factor 2 and 3 together, and factor 1 and 3 together. And by doing that, you manage to eliminate a significant percentage, in this case 50% of the possible combinations, because there are 8 possible combinations across all three factors, but by focusing on pairs of combinations, we're down to 4 rows in this array. Okay, now hopefully that's clear and everybody's able to see that. Now you might say, well, what about the missing combinations? So, for example, 1, 1, 1 is not in the table. That's true. It's not. And if you had some specific reason to think that there was some testing value in 1, 1, and 1, you could add it. But again, if you have a reason to think there's some specific value to a particular combination, a 3-way, 4-way, 5-way, or higher order combination, then that starts to suggest to me that you are actually dealing with a situation that has defined interactions. And if it does have defined interactions, again, this is probably not the right technique. You probably want domain analysis or decision tables as the technique. Okay, so now you might be looking at this going, all right, I get this conceptually, but I mean, what good is this? What am I going to do with it? Well, let's suppose that, let's see, I'm trying to get this to be a pencil. Let's see if I can get this back. Arrow pointer, laser pointer. Give me a pen tool. Okay. So let's say that this is operating system. Oh, it's a very heavy line there. So that is what it is, though. Okay, so factor 1 is operating system. And let's say that this is browser And let's say that this is connection speed. Okay? And for browser, I've got, let's say I've got, or for operating system, excuse me, let's say I've got Mac, and I've got Windows. And for browser, I have Chrome, and I have Safari. And for connection speed, I've got, let's say, I've got a low-speed connection, and I've got a high-speed connection. All right, so this little table now, what I have done is through a relabeling of the factor headings and by systematic replacement of options with specific values for a particular configuration factor, in this case operating system, browser, or connection speed, I've now got a situation where I've defined a set of tests, 4 tests, where I'm going to test Mac with each supported browser and Windows with each supported browser. I'm going to test Mac with each supported connection speed and Windows with each supported connection speed. And I'm going to test the Chrome browser with each supported connection speed and the Safari browser with each supported connection speed. And if there are any problems that are crop up, so for example, I've got Mac and it doesn't like Chrome, say, then I'm going to see that because that test is in there. And if I've got a problem that's specific with Chrome and a high-speed connection, I'm going to see that too because that's in there. They're in different rows, but I don't care. As long as they're in some row, they will be covered in a test. All right. Again, notice that if I wanted to test all possible combinations of these options here, there would be 8. But the only reason I would want to do that is if I were assuming that there's some specific weirdness that's going to occur with one particular browser, one particular operating system, and one particular connection speed. And theory and actual study show that that is unusual. Not that it never ever happens, but it's unusual. And if you are going to commit to testing higher order combinations, you have to accept that you're going to run an exceptionally large number of tests as the number of factors and options for each factor increase. And the value of that is limited. Okay, so this array is perfectly fine if we have exactly 3 factors and exactly 2 options for each factor, which is unlikely to be your situation. So what are you going to do? Well, you're either going to go find an orthogonal array from a reliable source on the internet, or you're going to use a pairwise tool. Now, I'm going to show you how to find the orthogonal array because it further illuminates what's happening here. Again, you don't just go and get these out of any sort of random repository, and don't think that you're going to build your own. If you are looking at this going, how hard could it be? I'm sure I could handle creating one of those things. You are pulling a Dunning-Kruger on yourself, and you need to stop. You don't know what a Dunning-Kruger is, and you can go look that up, but that's a belief that you have a capability that you almost certainly don't. Unless you actually are a mathematician by training, you probably do not know how to build an orthogonal array yourself. And I'll tell you, I don't know how to build them. And I've got no interest in learning how to build them because if I can find a reputable source, then I don't need to know how to build them. Just like I don't need to know how to make a steel jack to change the tire on my car if I've got a flat tire. All I have to do is know how to use the jack. So this is the same kind of thing. You go to a reputable source if you decide you're going to use an orthogonal array. Which I would say, if your company refuses to allow you to get the open source tool that I mentioned, the NIST tool, then I would just use the orthogonal array rather than shelling out thousands of dollars for one of these commercial pairwise tools, because I don't see any point in paying that kind of money for something that you could get for free. But more likely you're going to use the Pairwise tool, as I said. But let's go through this process of understanding how to use the orthogonal array in case you do need to use the orthogonal array, or just as part of better understanding what's happening behind the scenes here. So to go out and find an orthogonal array, for example, that university website that I showed you before, you go out to the website and you look for an array that meets the characteristics of the particular combinatorial problem you're trying to solve. So at first thing you have to do is identify, well, how many factors do I have? Okay, so the factors, again, would be configuration settings like browser, connection speed, and operating system, and so forth. Now, if you find an array that has more columns, like say you've got 6 factors, and you find the only array that you find that's going to work with the other characteristics of your problem has 7 columns, that's fine. You can drop the extra column. You just delete it. Now, in each of the columns, there will be numbers, usually starting with 0, but it could be starting with 1. So you have to count the number of unique numbers that are in the columns. And usually each column will have the same number of unique numbers. It's possible to find some that don't have that property, but it's unusual, and so probably not worth trying to find. So there have to be enough unique numbers in each column to hold the options for whichever factor has the most options. That might have sounded a little bit confusing, but if you think about what I did on the orthogonal array on the previous slide, you'll see that what you're going to do is a search and replace. Each 0 gets replaced by the name of the first option, and each 1 gets replaced by the name of the second option, and so forth. And so obviously you would need to have at least as many numbers as you have options for whichever factor has the largest number of options. Now, usually what happens is that 1 or 2 of the columns will end up having extra options. There will be options that don't equal the number of numbers, number of unique numbers in the column, and then so you'll have these numbers left over. And what you do is replace those. The tradition is to replace those numbers with a tilde or an asterisk to indicate tester's choice. Basically, it's up to you as the tester when you run the test to pick whichever configuration you want. It could be based on what's going to be easiest, or what's going to be the most popular kind of configuration, or what your marketing folks tell you they want tested more, or what your technical folks tell you they want tested more because they're worried it might break. It's up to you. Now, if you have done these 2 things right, then the third major bullet on this slide will follow, that there will be at least as many rows as the product of the 2 largest number of options. So, for example, let's say that you have 2 operating systems, 3 browsers, and 4 connection speed / type options that you want to cover. Okay, so you are going to need an orthogonal array that has at least 12 rows, because 3 times 4 is 12. Now, what's almost certainly going to happen is that you will find if you have followed steps 1 and 2, based on the number of columns and the number of unique numbers in each column, that you will actually have 16 rows, because there will be an equal number of unique numbers in each column, that is to say 4, and 4 times 4 is 16. But double check on that third major bullet to make sure that's the case. Now, if you might say, well, what if I screw this up? Will this just silently fail on me, and then I'm going to end up doing some testing, and I think I'm testing something, but it didn't test what I thought it tested? No. What will happen is if you make a mistake in applying the algorithm shown on this slide, is you'll end up selecting an orthogonal array that is either way too big or is too small. If it's too small, when you go through and try to map the problem onto the orthogonal array, what you'll find is that it won't fit. You'll end up with options that aren't represented in the table, or an entire factor that's not represented in the table, and you'll go, oh, no, I need to go back and do that again. If you select one that's too big, you're going to have a ton of tester's choice stuff, including entire rows where every option is a tester's choice option. And that's a dead giveaway that you probably need to go back and look for a slightly smaller, or perhaps much smaller, orthogonal array. Okay. So once you have selected the orthogonal array, you now map your problem onto the orthogonal array using the simple 5-step process that's shown here. You delete any extra columns, if there are any, and then you map the factors onto the columns. So you're basically going to add column headings. So this file that you get when you download this orthogonal array off of that website is going to be a text file. And if you import that into Excel, the import wizard will allow you to set it up, and you say, okay, well, this is how many columns I've got, and it'll pre-populate those numbers into the columns. You just add, at this point, you add a column heading on top of, or above the table which was imported. And at the top of each column, you put the names of the factors: operating system, browser, connection speed, security software, et cetera, et cetera. And then you go through and you do a select one column at a time, and you do a search and replace. So in Excel, you do Control-H, and you enter 0 as a thing to find, and then you enter the option name, say Mac for the first one, and you replace all, and then you do Control-H again, you say 1, and you're going to replace that with Windows 7, and you do that replacement, and Control-H again, and you replace 2 with Windows 10, etc. Now, the important thing here is that you do this on a column-by-column basis, because if you accidentally select the entire table, you end up screwing the table up. But this will be something you'll see immediately. So you go column by column, mapping the options onto each column, and then you check to see if there are any extra rows that do not have any interesting singletons or pairs. Now, by singletons, I mean the single options. And so is there any row that has just one option in it that's selected and is not present anywhere else? That would be kind of a warning sign, and you go, no, okay, well, maybe we actually need something smaller, because that's not actually showing any pair, but there might be other things that are in there. So you have to be very careful about deleting extra rows. If there are pairs in there that are actually present somewhere else, then you can delete those, but you have to be careful that you didn't screw something up. Usually what happens is that this happens with larger tables, and this is one of the reasons why using a tool is so helpful, because you will not get these kinds of extra rows that you have to go through and spend time trying to eliminate. Once you have done step 4, if that's necessary, then what you do is you populate your tester's choice cells with whatever configuration options that you want, which you can do now, or you can do it when you actually run the test. All right, so now let's take a look at how this works by looking at an actual example. So let's say that we're going to test the RBCS store on the website, so rbcs-us.com. And let's say that there are 4 factors that we're looking for that have 2, 3, or 4 options. So there's connection speed, and we're going to go either Wi-Fi, assuming like using a public Wi-Fi, so it's kind of slow and kind of glitchy and, jittery, or a high-speed wired connection. So really, fast and stable speed. We're interested in 4 operating systems: Mac, Linux, Windows 7, and Windows 10. For security software, we're going to test with the OS security software only. Danger, right? Don't do that, but we're going to test it that way. We're going to test it with Symantec. We're going to test it with Trend Micro. We're going to test it with McAfee. And I know I can hear you guys going, where's Kaspersky? Sorry, it's just a generic example. Don't take any offense. And then we have three browser options: Chrome, Internet Explorer, and Opera. Okay, so we got four factors, which means we need four columns. We have we need four numbers per column because operating system and security both have four options each. See that? You can't get away with less, even though you've only got two options for connection speed and three options for browser. You're still going to need four unique numbers per column because that's the only kind of array that's going to you're going to be able to map operating system and security factors onto. And we need 16 rows. 4 times 4 is 16. Now, back before I put that UK math department source up, there used to be on the AT&T website a repository of arrays, which I use, because AT&T was one of the original researchers of this. They took that down for some reason or another. I don't know where it went, but this is the array that I got from there. You're going to get the same kind of thing off of the Yorkshire University website. So you see it's columns of numbers, right? So that's what's shown in the middle of the slide. And what you do is you pull that into Excel, and notice there's 5 columns in there, so I deleted one of the columns because we had an extra column. And I put the 4 options on the top. Let's see if I get this annotation tool back again here. Yeah, so we got speed, operating system, security, browser. I also added this test column here so that I just had numbers for each configuration. Okay, and then I went through and I replaced, there was a 0 in this first column. I replaced that with Wi-Fi. And I replaced, there was a 1 in this first column. I replaced that with wired, and all the other numbers, the 2s and the 3s, I replaced with a tilde. See that? Now, for operating system, every 0 got replaced with Mac. No offense to you Mac users, but you pulled the 0. And you can see that there's Mac, 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 and since there's 4 options here, it fits exactly into this array. And then every 1 gets replaced with a Linux, and 2 gets replaced with Windows 7, and 3 gets replaced with Windows 10. Same routine here with security, OS only. That's the 0. Yeah. 1 is Symantec, 2 is Trend Micro, 3 is McAfee. And then for browser, we have 0 is Chrome, 1 is IE, 2 is Opera, and 3 is Tester's Choice. Okay, so then when I go to run my tests, what I do, let's get these annotations out of the way because they're going to look ugly, is I configure my environment to have a Wi-Fi connection on a sort of a hinky, not very fast Wi-Fi router, maybe some background stuff going on, other traffic on that router, so it's not real fast. And I've got this, I'm using a Mac to do this. I turn off any malware software or other security software that might be on there. So it's OS only, and I use the Chrome browser. Now, I run that test, and I go, okay, that's fine. Now, you might say the hard thing to change is Mac, is the operating system. I want to do all the Mac tests at the same time. So I could just easily skip down and go to test 5, which is my next Mac test, and go, okay, now I'm going to plug in a wire. I've got a wired connection, and I'm going to turn on Symantec security software on the Mac, and I'm going to use the Opera browser, and I'm going to see if I can access the RBCS website that way. Check that. And then I do my next Mac test, which is the test 9, and notice that I can choose either connection speed. Just for purposes of efficiency, I could probably just leave it wired, right? And then I do row 13, which is the final Mac test there, which is Mac with McAfee and Internet Explorer. Again, I don't care what the connection speed is, and because I've already tested Mac with the two connection speeds. Notice that I have in test 9, I have a situation where I can choose whichever browser I want to use on the test, and so I could just use Opera or Chrome or IE. Now, if I said, well, I'm going to use Safari, well, then that would actually add a 4th browser, and what you'd really want to do is replace every one of those tildes with Safari and test those combinations as well. So it's not a good plan to introduce new options that haven't been covered elsewhere, because if something weird happens, you're not going to know if that weirdness is due to the browser alone or due to the particular combination that you're using. Okay, so that's use of orthogonal arrays. Now, one thing I'll point out here is that we are assuming that these are independent, and I can do any combination that I want. Now, I didn't actually sanity check this particular array before doing it, but it might very well be that, like, maybe there is no IE for Linux. I'm not sure if there's an IE out for Linux. I mean, historically, Microsoft has been very hostile to open source software, and so maybe there is no IE for Linux. So maybe row 2 is an illegal combination. Now, in orthogonal arrays, dealing with an illegal combination can be kind of a hassle, because what you would have to do is you can't just replace IE with a valid value for the browser, because notice that IE is combined here with Symantec and with Wi-Fi. So what you would have to do is add an additional row or take advantage of the tester's choice options to try to engineer the valid combinations that are present in row 2 before you delete row 2 and the invalid combination of Linux with IE. So when you start to get those kind of constraints, this can be a hassle to do. Now, this is another place where the tool comes in. So if I've got the tool available from the National Institute of Standards and Technology, this ACTS tool, what I can do is very quickly go in and set up the configuration, as you see here. So the main window is there, and then I've said to modify a system. Usually this would be creating it, but I'd already created it. And so I've got a system here that I call RBCS Web Compatibility. You can see right here, that's the name I gave it when I created it. And here are my parameters, which are basically the factors from before. And the parameter type is what's called an enum, an enumerated type, which most of the time with this kind of testing is what you would have. And then we have the potential values that it can take on that are listed here. And the way that I created those is you add the parameters. The parameter values are here, and the parameter name and type is defined here. And you can just add them one at a time and add it to the table using this button down here. And you can have as many parameters as you want. I assume there is some sort of practical limit on the thing, but I mean, I've not run into it. And then when you go and you generate the tests using the tool, let's see, this annotations off of here. Come on. There we go. All right, you see here the tests that are generated. And we have 16 tests. Notice that the asterisk is used rather than the rather than the tilde in this particular case. But same thing, indicates tester's choice. The algorithm that they use to generate this IPOG algorithm, is apparently a little more stringent than the rule that is associated with an orthogonal array, because notice that we have fewer tester's choice options here. Now, that shouldn't really matter to you. If you want to figure out why and force it, you can use this tool and try to figure out a way to force it. But usually, tester's choice options are not something you're terribly worried about. Let me just go back to this slide for a moment and get it to do it. There we go. This tool has some cool flexibility that you're not going to get out of an orthogonal array, because on this tab right here, the constraints tab, you can go in and say this particular value for this, or this particular option for this particular factor cannot be combined with this particular option for this particular factor. So that problem that we had with the orthogonal array, where it had that Linux with IE combination, which might be disallowed, we can make that go away by putting a constraint here. We can also define additional aspects of the relationships between the parameters here. So it can be used to handle more complicated testing problems than a simple orthogonal array. Now, I'm not going to try to get into playing around with the tool here. And again, I don't know how many of you have an interest in using this tool versus an orthogonal array, or maybe some commercial tool that you've already got. But if you are interested in seeing this tool demoed in a more thorough fashion to handle these kinds of things, I am doing a free webinar tomorrow at 1 p.m. Central U.S. time. It's 20 minutes long. It's just a quick tool demo, so you can register for that at the rbcs-us.com website. And at that point, I will show off some of the features of this tool, including constraints and relations and so forth. So again, for those of you who are interested in using this particular tool, that'll be done tomorrow. Again, it's a free tool. I've got absolutely no commercial relationship with these guys. Not that any such commercial relationship would be possible, because they're a government entity. It's free to download. The webinar that I'm doing tomorrow is free. So this is just out of the goodness of our hearts. Feel free to tune in if you want. Okay, so what we have seen in this webinar is application of pairwise testing. Again, you want to use this in situations where you have independent options across multiple factors, and those options might interact, but they're not really supposed to. I demonstrated this using orthogonal arrays and gave you a practical source to get orthogonal arrays if you want to continue to use the orthogonal arrays, and some people do. The problem with the orthogonal arrays is it is a little bit more work than just using the tool, because you got to go out and do the search for the array itself. Now, that doesn't take a whole lot of time. And once you have located the orthogonal array, I don't think that the time spent in Excel mapping the problem onto the array is any more time consuming than using the tool. The tool is better for practical purposes, primarily because of its ability to handle constraints. So when you're dealing with situations where you are going to be constrained, it's a good idea to say, yeah, let's make sure that we use the tool. If you're almost never going to deal with constraints, then it's really kind of up to you. The tool, again, has the edge, and then it's faster than downloading the array. But it's probably, if you're not dealing with constraints, probably kind of a wash. Either way, it's a whole lot faster than trying to test all of the possible combinations, which is going to be an enormous number. Now, again, I want to re-emphasize something that I said a couple times, so I want to say it one more time here, which is if you are dealing with options that are supposed to interact, there's a predictable way of them interacting. You do not want to use pairwise techniques. I gave a talk the other day for a local group here, and I brought up the fact that I was doing this webinar, and somebody mentioned to me that they had a previous speaker who came in. The guy worked in a financial organization. He said that they did all of their testing using orthogonal array, so they or pairwise techniques, one of the two, and basically all their tests, all their input fields and so forth, they would use as pairwise techniques. And I'm like, are you kidding me? This is a financial application. There's predictable interactions between those fields because there's math being done in a financial application. They should be using a decision table or they should be using domain analysis because those are two techniques that are specifically designed to deal with numerical or condition-driven transactions. And the other technique, state-based methods, is something that you use where the system goes through a predictable series of states. This is one of the classic myths of pairwise testing, is that it can be used in situations where things are supposed to interact. Don't do that. Again, what you're trying to do is test for unintended interactions in a way that is manageable. It's not too many tests, but gives you a high degree of confidence that those unintended interactions are not there. When I say high degree of confidence, what is that degree of confidence? It's in the mid to high 90s. If you go and look at the studies that are out on the NIST website, as I recall, then this is consistent with the AT&T study on this, which was sort of the initial study to demonstrate the usefulness of this technique. Over 95% of unintended consequences of a particular option or a combination of options are associated either with a single option or with a pair of options. And the higher order combinations creating problems are very unusual. So pairwise technique is definitely one that you want to have in your toolkit. The other ones that I mentioned, decision table, state-based methods, and domain analysis are also very important. If you don't know how to use them, then a training course like our own Advanced Test Analyst course or some similar type of course that teaches you how to use those techniques is good, because if all you know is the pairwise technique, then it's kind of like the joke about giving a child a hammer and the whole world becomes a nail, which I think is what happened with the financial organization that I mentioned earlier. So good, powerful technique when used appropriately. Do not misuse in situations where it is not appropriate. All right, so I'm going to put up the contact info for us, which again, you see the website there if you want to take a look at our that webinar tomorrow. Let me clear these annotations. I have annotations hanging around here. At this point, I want to open it up for questions, and I need to figure out. Thank you. Okay, what do we got here? So I had a comment from somebody here, said nice. I think that was Marcella. So thank you. Glad you like it. Let's see. This one question. Shoot, that won't fit. Okay. I have a question here from Stefan. Is there any magic algorithm to be used, or before taking and using an already built algorithm, shall we analyze the best combination and create our own algorithm? What is the best way to uncover still possible errors that we might miss? I'm assuming, Stefan, you're referring to the algorithm that's used by the tool. There are, if I'm remembering properly, 4 different algorithms that it uses. I don't know the exact difference between them, and I don't really think it's all that important. As long as every pair of options for every pair of factors is represented somewhere in the table, then you're getting what you want out of it. Again, the important thing about the tool is its ability to handle constraints. which, as we saw with the orthogonal array, is not something that's real helpful. So tomorrow I'm going to demonstrate how to set up the constraints between them. As far as the different algorithms, again, I don't think, as long as you're getting all of the different pairs across all the different factors, who cares? Marcella says, even though I accessed it a little late due to a connection issue, this was very useful to me. Thanks, Rex. You're quite welcome, Marcella. Artem says, have I got it correct that higher order combinations greater than 2, in other words, triples, quadruples, quintuples, etc., are accountable for 5% of cases that we want to test? No, Artem, I may have misspoke or been less than entirely clear in my English. And again, I'm doing this from memory, but what my recollection is that the studies that have been done on the percentage of bugs, of configuration-related bugs that are due to triples, quadruples, quintuples, in other words, higher order combinations. Only less than 5% of such configuration-related bugs are due to higher order combinations, and most are higher order configuration combinations. Most configuration-related bugs will either be due to a specific configuration option. So, for example, your website doesn't work with Chrome at all. Doesn't matter anything else. It's just Chrome doesn't like it. Okay, but that's the majority, the vast majority of configuration bugs, which is why most people, when they're doing configuration testing, are perfectly happy to settle for equivalence partitioning only. But there is a significant number, not the majority, but a significant number that are due to a particular pair. So let's say Chrome with Windows 10. And so it is worth, if you're going to do some fairly complete configuration and portability testing, it's worth testing the pairs. But the number of bugs that you would find by going for triples, so let's say Chrome with Windows 10, but only if it's a relatively low-speed Wi-Fi connection, and then there's a problem, right? Or Chrome with Windows 10, but only if you're using McAfee security software, then there's a problem, right? Those combinations, they do happen, but they're pretty rare. And I could say from my own experience, I only remember one configuration-related bug that was due to higher order combinations. And I've done a lot of compatibility testing. I've managed years and years of projects that had compatibility testing as an element. I remember exactly one instance where we went live with this laptop that we had tested, and somebody plugged a particular network card into it, which we had tested, and plugged that into a particular router at a particular connection speed, and that caused the application that they were trying to run to crash due to a problem with the network. But it had to be those three things. And I told the folks at my client, I said, look, I mean, we can test for that. We can test for whatever you want, but the question is, how much money do you want to spend trying to do that kind of stuff? Yes, I get it was embarrassing that the salesperson felt like an adult when the laptop rebooted while she was giving a demo to the CTO at Bank of America. That's bad. That's not good that happened, but that's not really a risk that we can effectively mitigate because the cost of trying to cover all the triples would be too high. All right, hopefully I addressed Artem's question there. Artem says, can you give an example of when factors interact and why pairwise testing is not applicable here? Sure. So let's suppose that I have a credit card processing algorithm So it's taking, I'm doing a web service, and I'm processing credit card, and in addition to approving or denying the transaction, there are some other things I can do, like initiate a message to the vendor saying that's a fraudulent card, or initiate a message out to the card holder saying your card might be compromised, please call us. And let's say that there are a number of conditions that interact here, like the amount, if it's over a certain amount or under a certain amount, that's relevant. The cardholder name, the card verification number, matching or not matching, the location being a typical location or a possibly okay location or a definitely probably not okay location. So I've got like 4 or 5 different factors. And those are all can take on 2, 3, 4 options. And they all interact in a very specific way for the algorithm to make a decision as to whether to approve or decline the purchase. Because usually those things are not entirely driven by is there available credit. Obviously that's part of it, but there are other parts other elements, other factors that come into that decision. And the way that those interact are defined by business rules. So if you just test random combinations of pairs there, then that's not going to necessarily discover particular combinations that are combinations across 3, 4, 5, however many factors that have to be a specific way to trigger a specific action. Okay, so that's an example of where this technique would not be useful. Vasily said, I misheard the last technique along with decision tables and domain analysis. It's state-based or what? Yes, it is state-based testing. So state transition tables, state transition diagrams, switch coverage, those are all variants of state-based testing with various degrees of strength. And state-based tests are useful when you're dealing with a system where the behavior changes based on events that have happened in the past. So there are certainly plenty of things that exhibit that kind of behavior. So for example, a lot of websites need to keep track of whether you are logged in or not, and the behavior of the website changes whether your state is logged in or not logged in. And you might even be logged in with different privilege levels, and so that can also change what you see and what's accessible to you. So when you're dealing with a system where that which has happened in the past affects the way the current conditions and events are supposed to be processed, you need to use a state-based technique. Olga says, thank you, Rex. You did a very good point about pairwise testing in financial organizations. Next time I will reference you when my boss tells me I should use Hexawise. Well, I mean, my issue with Hexawise, of course, would be twofold. First off, yes, if you're testing a banking application and you're just randomly testing combinations, which is really what it is, right? It's random. The specific combinations across all the factors is basically random because it has to do with the way you assign the options to the order in which you assign them as to whether any one particular combination across all the factors is there. If you're just testing this random collection of configurations that is guaranteed to contain, or inputs or whatever, that's guaranteed to contain all pairs across all options, but that's the only thing that's guaranteed, you're basically you're doing it wrong. As financial applications, things are supposed to interact, and they interact in predictable ways. There are math and accounting and other kinds of rules that determine how they're supposed to interact. So first off, yeah, you're doing that wrong. Second off, why buy a commercial tool for doing pairwise testing when there's a perfectly good free one out there? So I mean, I get that you at this point have bought it, but you don't have to renew the license. Pablo says, thank you very much for the webinar. Can you please repeat the 3 analysis techniques where there are more predictable interactions like it happens on financial organizations? Decision tables, domain analysis, and he also missed the 3rd one. So that was state-based testing. I guess maybe I was mumbling or something when I said that, but hopefully it's clear now. Olga says, thank you very much, Rex. The topic covered is clear, precise, and succinctly covered. Therefore, no questions from me. Well, you are quite welcome, Olga. Artem says, thank you, Rex, I assume for my answers. Let's see. Trying to see if I've got any other questions here that I have not addressed. Looks like I've gotten them. Let's see. Yeah. Oh, okay. So here we've got something from Peter. Doesn't the market share matter a lot? I think this was in the context of choosing the tester's choice values. And yes, absolutely. So market share, if you're saying, well, you know, we want to heavily test with a particular configuration value because most of our customers are using it, then that makes perfect sense. And it continues. Mac Safari and Windows Chrome is a much more popular configuration compared to Mac Chrome and Windows Safari. Yes, that's true. But let me just make a point here for you, Peter. That the purpose of the exercise with the pairwise technique is to look for unintended interactions, and that includes looking in places that might be a little obscure, okay? Now, the question of how important it is, you know, that's up to you. So you can certainly, let's say the pairwise tool generates 100 rows, say, just, you know, as an example. It could be unusual, but that's, you know, 10 options per factor, you know, so you could end up having something like that. What you might do if the number of rows that the tool generates is greater than what you can actually test is you go through and you just sort of rate them or rank them based on how important is, you know, any one of the pairs in this row. How the common combination is it? And then you just bubble those up towards the top. And then you start at the top and work your way down. And if you don't get to some of the combinations, and, you know, as long as they're like, yeah, you know, those are pretty obscure, no big deal, then that's fine. Okay, I think all of the questions have been addressed at this point.
Yes, I guess we are done with questions. Rex, thank you very much for participating tonight and for your presentation. And guys, thank you for listening and for your questions. I hope you've enjoyed listening to Rex's presentation, and I do hope that it has been interesting and useful for you. We will appreciate if you answer a short questionnaire. You can see it now on your screens. And one more time, thanks a lot, and stay tuned for our future events. Good night.